Hello, I'm Chris Eschler, and for my 3017 final project, I'm going to be using Mathematica to model and optimize the design of a dichroic mirror. The objective of this project was to model the light transmission and reflection properties of a dichroic mirror, and to optimize it for cost within a set of performance constraints. The application is to isolate the excitation signal of a fluorescent drug that would be injected into a patient's brain. So there were a couple of design criteria that were used for creating the dichroic mirror. For one thing, this would have unpolarized light incoming at a 45-degree angle, and it needs a reflectivity of at least 99% for light of wavelength 594 nanometers, and a transmissivity of at least 90% for light at a wavelength of 473 nanometers. The reflectivity is important because that's actually what's going to allow the signal from the drug fluorescence to be picked up. The other thing is this is intended to be produced via a sputtering process, so layer thicknesses need to range somewhere in 1 to 50 nanometers in order for that to be a viable way of producing them. And you want about fewer than 15 or so layers so that it's not too intensive a process to create. So this is a sort of schematic rendition of what this type of dichroic mirror would look like. In this case, there are four bilayers. Each one has two layers of material, each with a different index of refraction. And in this case, they also happen to have different thicknesses, and it's all deposited on top of a substrate. So at each interface, light can reflect or transmit into the next layer, and as a result, various wavelengths of light will have different properties for reflection and transmission through the dichroic mirror as a whole. So first of all, Mathematica was used to develop a model for light transmission and reflection. This was based on transfer and propagation matrices that were derived from Maxwell's equations using the boundary conditions at material interfaces. So matrices were combined via matrix multiplication to create one overarching matrix that the information could be plugged into to give the output of the reflective and transmitted components of the light. And in this case, absorption was neglected to make the problem easier to solve. Some of the code that's shown here includes a function to determine the angle at which light will propagate through a layer given its index of refraction. This is just based off of Snell's law. And further down, these are actually the matrices used for transfer between two layers and propagation through a layer with transverse electric polarized light. So all of these are combined into one large matrix which actually determines the overall properties of light transmission and reflection through the dichroic mirror as a whole. The same thing is repeated with transverse magnetically polarized light below. So the big obstacle in this case for figuring out the design of the dichroic mirror was material selection. And the material selection started off with an initial range of possible materials that could be selected from. This included cryolite, silicon dioxide, cerium fluoride, silicon monoxide, zinc sulfide, bismuth 3 oxide, germanium, magnesium fluoride, polystyrene, lead 2 fluoride, zirconium oxide, titanium oxide, silicon, and tellurium. But as this was going to be used in a biomedical application, the first filter from these materials was to find materials that would be suitable for use in the brain. So that required low health risks and things that would be stable within bodily conditions and not produce any toxic byproducts from decomposition. So that essentially filtered it right down to 7 materials: silicon dioxide, polystyrene, silicon monoxide, zirconium dioxide, titanium dioxide, germanium, and tellurium. All of these materials were determined to be safe for use in the brain and were carried on to the next step of the material decision process. So the next step was to try to optimize for cost, and to do that, it was decided to essentially drop the two most expensive materials, titanium dioxide and germanium, because they're about an order of magnitude or two more expensive than anything else on the chart. So it's clear that even including small amounts of them in the final product would significantly drive up the overall cost of production. In order to have a way to compare all of these materials, it was determined the number of dollars per nanometer of thickness per square meter of deposited layer that each material would cost, based off of bulk prices from Sigma Aldrich. And most of these prices were quoted for an amount of material on the range of 10 to 100 grams. So enough for a starting run for some kind of lab scale experimentation. And from this, it was found that silicon dioxide was the cheapest. Polystyrene, silicon monoxide, zirconium dioxide were all in the same order of magnitude. And then tellurium was a bit more expensive than that. And then, like I said, titanium dioxide and germanium were the most expensive materials. In addition to that, the index of refraction of each material becomes extremely important for this application. So all of those are listed here, and the materials are ordered from lowest to highest index of refraction. So moving on from the materials, it was necessary to determine how many bilayers would be required in order to get the optical properties that were desired. So a number of materials were weeded out as suitable for this application, and that included mostly tellurium compounds, or not compounds, but material combinations that included tellurium and one other material, such as tellurium and silicon dioxide, tellurium and polystyrene, tellurium and silicon monoxide, and tellurium and zirconium dioxide. So of those materials, each one was tested to determine which would have the lowest cost while fulfilling all of the design criteria laid out previously. And the way to determine that was based off of the plot that's shown here. This is a plot of the thickness of the tellurium layer on one axis and the thickness of the other layer on the other axis. In this case, it's zirconium dioxide, which ended up being the cheapest material. So what the plot shows is at a given number of bilayers, which is being controlled by this slider up here, it's currently 3 bilayers. The plot will show, it will plot all areas that fulfill the transmission and reflection criteria for the mirror as a whole. So 3 bilayers don't fulfill the criteria at any of these ranges of thicknesses, but 4 bilayers, you can see some of these small areas which actually do fulfill these criteria, and when these plot, this actually produces a contour plot which gives the price per square meter considering the power required to deposit it, the bulk materials, and the labor required to run the machinery. So this ranges from $4 to $10 per square meter within this regime of like 0 to 50 nanometers per layer. And the minimum thickness for the minimum price was determined by looking at these graphs for various combinations of materials and then finding the lowest point. So here it's about $3.75 per square meter, and that's at this combination of thicknesses. And so the 4 sets of values here are the thicknesses found for combinations with tellurium and another material. And you can also see as you step up the number of layers, there is a little bit more freedom in which combinations of thicknesses will be effective for this purpose, which makes sense. But it also increases the cost per area because of the greater total thickness. So from there, the next step was to put together a couple more variables in order to fully optimize the system. So this manipulate is capable of changing material for layer 1 and layer 2, the number of bilayers, the thickness of layer 1, thickness of layer 2, and the thickness of the substrate on which it's deposited, which we modeled as a glass substrate. In this case, it's 0.1 millimeters thick. All of these numbers can be adjusted, and the cost graph shown here will change. This is the schematic representation of the system, and then the transmission and reflection graphs shown here as a function of wavelength. So for time purposes, I've already run a number of these from the most effective thickness combinations for a couple of different material combos. So here is tellurium and silicon dioxide. You can see it's about 30 and 24 nanometer thicknesses, and the dashed line here is 473 nanometers, so that's the transmission condition, and here is 594 nanometers, the reflection condition. You can see that they have high transmission, high reflection at these two wavelength values, exactly as desired. And to step this forward a little bit, this was the optimal combination, which was tellurium and zirconium dioxide. So much thinner layers, which actually allowed this to be cheaper overall, despite having slightly higher material cost per volume. And you can also see that they have very high performance in the exact wavelengths that are specified for this application. But it's also very specific to that wavelength because you have quite a peak structure here. So that becomes important in a little bit, analyzing the downfalls of this method. So essentially, the two graphs are the main output from this, where you can see that they're fulfilling the criteria that have been set out. The limitations of the model, for one thing, it assumes there's no absorption of the light by the material, so transmission and reflection add up to 1. And it's also only calculated for transverse magnetic and transverse electric polarized light. So in reality, it's unpolarized light that's being fed into this dichroic mirror, and we basically assumed that if both transverse magnetic and transverse electric met the criteria, then the unpolarized light would do the same. The other thing is cost figures are very approximate. They consider labor, power, and raw materials for each type of sputtering condition, but it would be helpful to get much more specific details about the costs in order to actually determine which material is the best for this purpose. And then, as was shown earlier with the very thin peaks on the graphs, the resultant films are extremely sensitive to deposition thickness. If the thickness of one of the layers changes slightly, it can shift the peaks on the graph to the point where the criteria set out are not being fulfilled. And so it's very hard to control those specific things in a sputtering type process, which means that you might want to design a film that has a little bit more leeway in terms of thickness of each layer. And then the overall conclusions that I took from this model were that the most effective material combination was 12.4 nanometer thick tellurium and 16.6 nanometer thick zirconium dioxide in 4 bilayers. And that produced the 99% reflection and the 90% transmission as desired. But there were several other combinations with tellurium, namely silicon dioxide, polystyrene, and silicon monoxide, that actually had similar properties and also had a relatively close cost within about 30 or 40%. So all on the order of $5 per square meter to produce. So it's possible that one of these other three could also be the most cost-effective contender. And finally, these works were very helpful to the production of this model, including the economic analysis of the deposition of electrochromic tungsten dioxide. And I would like to acknowledge some of my team members from my 3024 group for their help in producing some other parts of the code and also for determining a lot of the material costs that went behind things. Thank you.